The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thank you for joining us for today's webinar. This webinar is entitled Weather Services for Sustainable Winter Road Maintenance Operations, and our presenter is Chris Albrecht, the Director of Business Development and Consulting Services with the Narwhal Group. My name is Joe Alloway, and I am here as the administrator representing the Center for Environmentally Sustainable Transportation and Cold Climates, CESTiCC. And we'd like to invite all listeners to, if you have questions while the presentation is going, please hang on to them. There will be about 10 minutes at the end for question and answer. This webinar will also be recorded. So anybody who desires to download it or share it at a later time, it will be cataloged and archived on the CESTiCC website, CESTiCC.uaf.edu. Thank you all again for being here, and without further ado, Chris Albrecht.
All right, thank you very much, Joe. As Joe said, my name is Chris Albrecht. I'm the Director of Consulting Services and Business Development for a very small engineering firm, technology firm out of Salt Lake City. And I'll get into that a little more, but I wanted to, first of all, thank my co-authors on the chapter of the book that this series of webinars is based on. We're chapter 5. We're talking about the weather services end, which is the weather sensing, the operations side of the weather that feeds into all the other services that are discussed during this webinar series. Lee Sturgis and Ralph Patterson are co-workers at the Narwhal Group. In fact, Ralph actually just retired out in Salt Lake City. Lee is up in Bozeman, Montana, and I'm actually in Iowa. So outside of Des Moines, Iowa. We are a small company once again, but we do a lot of tech consulting in the west part of the United States and up into Canada. So which has given us a really good background on not just the operations side, but the road weather instrumentation side. So you'll hear a little bit about that, and I'd be happy to answer any questions at the very end on that. Now, when it comes to the meteorology side, I'm not a meteorologist, so just to warn you, I can forward those questions on to Lee Sturgis. So I just wanted to note my co-authors on the chapter. And one more thing before we get started, I wanted to thank the university and the centers and TRB Committee on Winter Maintenance, which I'm a member of, for hosting this webinar. I think it's a new area. I don't think anything like this has ever been done. There's never been a textbook on winter operations before, and it's neat. There's a lot of money that goes into winter operations, which we're going to talk about. So thanks to all these groups for recognizing the importance of this topic. I want to give you a quick outline of what I'm going to talk about in the next 45 minutes or less, hopefully. I'm going to try to keep it a little bit short, let you guys ask me, let everybody out of here a little earlier. I'm going to talk a little bit about the background of what is the introduction of the chapter. Some road weather basics. What is road weather versus weather? Talk a little bit about meteorology. The asterisk is there because I don't know anything about that. So I'm going to just comment before this. You'll probably notice that. Then we're going to talk about actual operations, what happens when folks or agencies do employ these methods. Talk about road weather information systems, which is the road weather technology, data gathering piece of the operations that many of you are probably familiar with. If you work for a state agency or even a consultant, you might know that there's systems of road weather instrumentation out there, numbered in the thousands across the country and across the world. Then I'll take some questions from the group as you at the very end. So please note down your questions, because it's a one-way me speaking to you, and we'll just leave them towards the end if that's all right. Thank you. Let's get the background. Winter weather, as we talk about in the book, and I think as the previous speakers in this series have talked about, it's a global issue. Millions of dollars invested just by each agency involved. So you can think of 50 states, you can think about the countries around the world. It's a billions of dollar situation, and not an industry, but a field that requires a lot of money to keep folks safe and keep them moving, keep the economy moving. All the reasons that Zhao Ming had mentioned back in May when I listened to his presentation. This is a safety, it's a traffic flow, and it's an economics issue. And obviously, when talking about weather operations, those patterns and the types of weather, they vary considerably week to week, season to season. We've seen that with weather patterns, different years, the polar vortex and things shifting around. So that's an example of not only the weather changing from week to week, season to season, but the actual weather pattern shifting, not just those extreme events. And I'll talk about a little of that later. To minimize this, a lot of agencies, I'd say the majority of the northern states, so that 40 plus states that Dr. She had mentioned in the first episode that I watched, northern tier states, everywhere from northern Texas and northern Alabama, Georgia, to everything else in the United States except maybe Hawaii, that employ winter operations. Now, every state has seen snow, but the ones that see it regularly enough to impact and spend significant amounts of money on materials and equipment, those are the ones that we really want to focus on, and those are the ones that employ specialized weather services. The examples go from states like Utah, who have an embedded weather service that really helps them with operations and weather forecasting, to states that are new to this world and trying to optimize their operations. And I just wanted to mention the other thing, the background that we talk about, is that road weather is not the same thing as weather. Weather is atmospheric weather. It's what the AMS talks about. It's what news agencies say. It's what's going to happen in general, more terms. What we're talking about, what's going to happen to the road surface. So traditional atmospheric road forecasts are really important. The forecasts are really important. But the operations on the road, we really want to look at the impacts of that weather on the roadway, because 2 inches of snow can have a big impact to a northern and a southern state like Georgia, and it can have very little impact, depending on where you're at, depending on the timing of that snow, and the temperature of the road, and etc. There's a lot of factors that contribute in. In the very end, I want to go through fairly quickly at the end if I don't have as much time, are some of the technologies that are going to be that have really impacted the way the world is working when it comes to weather ops. Okay, I wanted to talk about weather operations. When I threw out this presentation, when I talk about these operations, I described them. I want to talk about, I mentioned how costly operations can be. You're looking at a fleet of vehicles here out in Utah. The gas, the materials, the time, all that's millions of dollars being spent nationally and in each state on this. So one thing I wanted to stress is that the cost of these operational services, the forecasting, pavement specific forecasting, and all the things that companies like mine do, they're just very, very small to invest to see the benefits. A month of a service at a location doing weather forecasting on a stretch of roadway, it saves a couple hours of staff overtime. That's all you would need to do to see the benefits of that. So there's a lot of terms we talk about the benefit and cost of this. It's just, you don't have to save a little bit of salt to really pay for a lot of services, or a little bit of overtime or making changes. So these services actually extend from DOTs actually to airports and other operations as well. So what I want to point out is the benefit cost. But to look at it as a cost along those costs. And those costs are not only just direct costs to the DOTs or other agencies, there's environmental impacts as well. So the whole reason we want to save salt is to not spend as much on salt, obviously, but not to also to put as minimal amount of salt in the environment as possible. So getting now to weather variables, as we talk about, we're influenced by a lot of big picture global weather patterns and seasonal weather patterns. But I think, as I mentioned earlier, with the polar vortex that most of us have heard about, we're seeing more extreme weather events caused by shifts in patterns, of course, and then just the amount of energy in the atmosphere, whether who caused it or whoever's the cause behind it. I think we can all agree we're starting to see some really swirly looking weather out there. And in my job as TRV, Winter Maintenance Committee, I have hosted sessions on this topic, and we try not to talk about who caused what and what's doing this, but we all can agree on there's some really, really crazy weather events going on, whether it's severe rain, severe cold, just amounts of precipitation we've never seen before, and the extremes of temperature, and that can be directly related to more energy in the atmosphere. So that's really what we're seeing as the first thing that pushes the big scale things that are happening in the environment. Then there's local and regional factors, of course. Snow and ice covered roads, they vary location to location. You know, one snowflake can cause a much different situation depending on where you're at regionally and how things operate in those regions. In addition, your latitude, that winter sun angle, topography, mountains versus the flat place like Iowa where I live, and proximity to ocean, the land masses, the maritime areas versus the continental climates, and humidity and those sort of things. That can make a big difference. So being a researcher that I am, and I came from a research background before consulting with State University, where I helped run one of these programs, these UTC programs like yours. You coming from that background, you realize that when people ask for a solution, it really depends on who you are. So building a solution for just a DOT or all the DOTs in the United States is not easy, because there's a lot of different climates and everybody has their own. There are no two states that are exactly the same, no matter how much you might think that. Therefore, similar size meteorological intensity of events can make completely different results, obviously. Now, like I said, that 1 inch or 2 inches of snow can be not a problem, or it can be devastating. So if you look on here, we're talking everywhere from ice on the road accumulating to just the slush to fog to what I call, and I'm going to try to move this thing out of the way here because I'm not sure if you're seeing my part of my screen, but over on the far, there's a difference between snow and road snow. Snow is the stuff, the fluffy stuff that collects on the side of the road, and road snow is a real pain in the butt. Road snow is stuff that can pack down. It has a different characteristics, and it behaves differently because it's on a paved surface rather than on grass or dirt or whatever it may be. So we know that surface can change considerably based on not just what falls on it, but what the status of that surface is. Hold on, I'm trying to go to my next slide. Oh, there we go. The second area I want to talk about now, I've done the introduction, is the kind of basics of road weather. Road weather, according to the American Meteorological Society, is apart from regular meteorology and atmospheric science. It's the specific application of all the weather observing, modeling, and forecasting that they normally do, but it's applied to the road surface and the driving environment, and how that impacts the driver, the vehicle, and the overall traffic patterns, safety-wise, economically, and operations-wise, as I mentioned earlier. Other terms we've used for this field are surface transportation weather, transportation meteorology. It doesn't really matter, but it's the whole idea that we're taking that broad atmospheric view of forecasting and bringing it down to the road surface. So it's really very much a process, road weather is. One thing also, because I come from a research background and I work not just in road weather, but worked in road weather, transportation technology and safety, there is this very important concept of the relationship in all of transportation, especially transportation safety, that talks about the driver, the vehicle, and the road. Those are the three, pedestals of the footstool, if you will, that create a safe environment or a problem. The driver, how attentive is the driver, what's happening to the driver, what kind of skills does the driver have, and then what's affecting the driver. And for example, visibility. Visibility when it comes to weather, when we apply this driver vehicle road model to road weather, we're really talking about things like visibility, whether it's fog, whether it's really heavy snow, blowing snow, whatever that may be. And then on the vehicle itself can operate differently in different kinds of weather, but it's really where that vehicle does touch the road, and other things like wind blowing on the force on the vehicle impacts the performance of the vehicle. And then the third leg of the stool, of course, is the point of contact, the wheels, and the road surface. That road surface, getting down to what is happening between the tire and the concrete or the asphalt or the gravel. What's happening there, and how is that affecting the safety of the vehicle? So I just applying that driver vehicle road concept when it comes to safety, applied it to road weather. We have those same three needs or elements. Talking about wind and pavement conditions, getting further into the road piece of that three-legged stool. It depends considerably on things like the surface temperature, but also, which we all kind of agree, surface temperature is really important. And then when I hear folks talk about, we just really want to know the temperature of the road surface. That it is important, but you can't leave out the importance of subsurface temperature, because that subsurface temperature, whether it's higher or lower than that road temperature, and the trend in those temperatures really will impact that road surface quite a bit. And then when you add on top of that, the third bullet here, the development of liquid or solid water, what's falling on the surface. You can have a snowflake fall on a piece of concrete at 32 degrees, and it will melt if the subsurface temperature is higher or going up, and it may freeze if the temperature of the subsurface is going down. So all those three elements really impact, and knowing and understanding that thermodynamics, if you will, of the roadway surface is really, really critical to be doing winter road conditions, road operations well. Talking about the pavement temperature then, it's very sensitive to subtle changes, whether it's the sunlight or whatever it may be. So we do things like thermal mapping. Thermal mapping you may have heard of as transportation professionals, where you go and you look at the temperature, road temperature, surface, and typical conditions of the roadway. Because a lot of roadways can vary from point A to point B over 100 yards, depending on shade and different characteristics of the soils underneath, the thickness of the roadway. That can vary. Very, very seldom is it uniform over several miles. But knowing that cross section, knowing that under that thermal mapping, if you will, of your roadways is very important to understanding what's going to happen when that 2 inches of snow falls, or that 1 inch, or if it rains. And if it rains in December, if it rains in November versus raining in March, it can be a totally different ballgame. So, talking about the winter precipitations, once again, I'm talking about snow, the blowing snow, which can happen well after the end of an event, rain, and then freezing rain, and things such as grapple. I think you folks up in Alaska know what grapple is, ice pelt sleet. But each is very important to understanding how they can significantly alter maintenance plans. Understanding what's falling, and then what's falling, what it's going to turn into an hour from now, 24 hours from now, so forth. That can change your maintenance operations considerably. Oops, I keep hitting the wrong button. So then the non-precipitation road ice concerns. I mentioned wind earlier. Not only affecting the vehicle, but the blowing and drifting, which can be obviously a huge problem. Frost, depending on, and we'll get a little bit into the atmospheric part of it, but the water vapor depositing on the road. Humidity, that can really impact frost and make, once again, something happening not during the event, if you will. The storm happens from 8 a.m. to 3 p.m. This stuff can happen well after the end of the storm, the quote-unquote end of the storm. And then melting and freezing ice, more dependent on the time of day, more depending on the sun angle and the solar radiation. You can get wet, frozen, wet, frozen, wet, frozen cycles quite a bit. And then we've all heard of black ice, but also is very much related to the melt and freeze cycles of roadways. So well after that precipitation falls, whether it be snow or rain or one of the others, these other factors can contribute to an operating plan for winter maintenance. I'm going to talk a little bit about my least favorite area of this book, I guess, only because it's fascinating, because I don't know much about the meteorology side of it. But want to talk a little bit why meteorology is important to understand when it comes to road weather operations, and also how in big picture how it works. But there's a lot of conditions that impact the environment, as I said in the opening. We consider everything from the soil through the pavement surface, the atmosphere is directly above. So it's that microclimate, if you will, around the roadway surface. So at the pavement surface state, it all depends on the surface temperature, subsurface temperature, and the deposition of whatever that liquid is on the surface. But when we talk about road weather, it's not just that surface I already mentioned, it's the near surface atmospheric state. In general terms, that 10 meters around or above a roadway to the 10 or 15 meters on either side of the roadway is what we call the road surface environment. And as most of you know, as snow falls, as sleet happens, as rain, it hail happen, things can really change quite a bit from 50,000 feet to 30,000 feet to 10 to 5,000 feet. It can change, in a city outside of Seattle where we work, one side of a city with a lot of topography can be snowing, one can see rain. That change, that difference, that dynamic state of the weather goes all the way down to the area right above the roadway because of spray, because of heat islands in cities, because of the thermodynamics of the actual pavement itself. That can change considerably what's going on during that last 10 meters as something falls. So that's something very important to understand and keep in mind moving forward. Talking about the near surface atmospheric state, excuse me. I'm going to talk about synoptic weather patterns, which is the really big picture weather, the big cyclones, if you will, that go through. And I, as an Iowa State graduate, our mascot is a cyclone, and for the longest time, and I think most people think a cyclone is a tornado. Well, a cyclone is much bigger than a tornado. A cyclone is a big storm that's revolving counterclockwise for the most part, that's revolving and moving into an area that affects weather over a large period. So as you see high and low pressures come in and weather impacting, you keep an eye on things, and that's that first lead into a good weather forecast. But then we fairly quickly get from where's that big weather pattern coming from and going to, how much energy does it have? We then get down to those local weather phenomena, the wind, frost that's been occurring, fog, the cycle, the lake effect snow, the black ice, solar shading. All those things are actually impacting the roadway. So instead of looking at the state of Alaska, we're going to get a lot of snow over the southern part of Alaska. What's going to happen on those roadways? We're going from an area to a place, a much smaller area, a point, if you will, or a line that's being impacted by the weather rather than an area. So those thought processes change considerably depending on what that may be, what types of those local weather phenomena are present. Speaking now to the fourth area, now knowing a little bit about weather, knowing that we work from a process, a funnel, if you will, in weather forecasting from what's the big cyclone coming through, what's the weather looking at a regional state, what's going to affect the roads that might be in a valley, might be in a mountain, might be in the plains, whatever. World weather forecasting operations really takes that and applies it to specific clients and specific situations. For example, my company works for the Utah DOT. We do all the road weather forecasting and travel information for the state of Utah. Do the same thing up in the state of Washington, British Columbia, Wyoming, a bunch of states out west. We usually do that is they need that special additional help coming from the weather forecast and figuring out what that impact is going to be on the road. We use the word impact quite a bit throughout the next several minutes of this presentation. So for the most part, private companies, sometimes government forecasting organizations produce road weather forecasts. Sometimes they're quasi-government, quasi-private sector. Some states have employed their own meteorologists that over time learn road weather forecasting. There aren't a whole lot of folks coming out of school that have actually learned road weather forecasting, but on the job or working for a private sector, you can get more experience looking at the actual impact of that weather on the roadway, which is once again different than atmospheric forecasting. So we have both models and several models within the U.S. alone. Organizations can be embedded within an agency, as ours is in Utah. A lot of people think our employees are Utah DOT employees. Well, they're actually working closely with the Utah DOT to help them out. Either way, those organizations have that close working relationship and that's the only way it works is if you have that close working relationship, whether it's a remote forecasting group or somebody embedded. And those forecasts have to be as detailed as possible, and then have to be over time learned that what that forecast means converts into actual operations and maintenance actions, whether it's salt you put down, whether you're not putting any salt down, all de-icers, plowing, all that. You're building that relationship and understanding what does this mean. That's key. And over time, that really does work. And I think the state of Utah and other states are examples of where they've really saved lots of money, saved a lot of lives, and saved a lot of time by learning to work together and understanding how the weather is coming relating to the road and what's that impact going to be. I'm going to take a little bit about forecast scales. I left in a lot, and you see throughout this presentation, I left in a lot of text from the book because I think these slides are going to be useful. I'm going to give the slides off. They're useful as a little primer, if you will, in road weather. So I like to actually present from pictures and talk a lot about pictures, but in this academic sort of setting, that's not really helpful to people later on. So forecast scales, I'll talk a little bit about what those are and the importance of each. What's a nowcast is a 1 to 2 hour really short-term forecast that's highly specific to rapidly changing weather. So we know that the temperature is going to drop right at nightfall, for example, out in the Salt Lake Valley, and what's happening right now with light rain, boom, at 5:30 or 6 or 9 o'clock at night or whenever that may be, it's going to convert over to snow and more, and it might even become more intense depending on what else is going on in the atmosphere. So that nowcast really is that short 1 to 2 hour forecast that helps you understand the big changes. Once again, 2 inches of snow over a 24-hour period is much different than 2 inches of snow in an hour. And then you add in the complexity and the differences in what the road surface can be. You can then understand some of the potential issues. Operational forecasts are what we provide daily. Those look 36 to 48 hours out, and it's getting people prepared more for the immediate future with a storm right before it hits. Extended forecasting then is out to a week, looks at basic planning, situational awareness, planning, staffing. Somebody might take off vacation and they're not going to go on vacation and they might cancel plans, and we might say, hey, we need to put a warning out through the National Weather Service or whatever it might be. Seasonal outlooks, companies like mine and many others, of course, do seasonal outlooks looking ahead several months. And everybody I talk to always wants to know, how much is it going to snow next year? How bad of a winter are we going to have? And we can say better or worse in a lot of cases. We're not going to tell you when it's going to snow. But those seasonal outlooks can give people more long-term planning horizons to use in their operations. Excuse me. One of the tools that when we now get into the operations and doing forecasting for a DOT, for example, and I'll primarily talk about DOTs as the client. DOTs, like I said, can be airports, they can be private construction companies. A lot of people use pavement forecasting and road weather forecasting, but I'm going to focus on the DOT as our primary client. There are a lot of, we do pavement modeling, for example. Pavement models are probably the most valuable tool to an operational manager at a DOT because the exact temperature of the roadway right at this second is important, but what's more important to a manager or anybody predicting operations is what is the trend be. If you're going from hot to cold, cold to hot, you're hovering around the same temperature, predicting those and using pavement models will give folks a much better idea of how they're going to react and what materials they're going to use. Whether they're going to use more materials right away, delay putting materials on, whatever that may be. But it's combining the soil temperature, that subsurface temperature I mentioned, pavement conditions and temperature, and then atmospherics, plus a forecast of what's going to happen on top of that to determine how is that pavement going to look from 1 hour to 2 hours. Here on this slide from 30th of March from 6 a.m. all the way to 6 p.m. What's going to happen to that temperature of the roadway, and also taking into consideration what you put on that pavement to help fight the ice and snow, and what's going to happen with sunlight and every other. So we're trying to put this long-term trend together so people can understand, that the operators can understand what's going to be happening most likely. So essentially, it's a high-resolution forecast of the surface over the near term. Longer term, as with anything, predicting something in the next 6 hours versus the next 6 weeks is much easier than the short term. One of the models you may have heard of, and this is something that affects at a big level that we use to kind of initiate all of our modeling, any of our forecasting, is called Metro model. It stands for the model of environment, temperature, and roads. But that model is used widely in the U.S. and it's used widely in the U.S. in Europe for maintenance decision support. So that's the model, that's underlying model that much like when you get a forecast, whether it's on AccuWeather, you're on your phone, there's a model doing all that prediction. It's not always just a person sitting in a room sticking his finger in the air and going, I think it's getting colder. There's a model that takes in all the observation data and plugs that into a model and helps predict. So anytime you see a weather forecaster on TV, he's showing the storm tracks or whatever it might be. That's all products of models. And you know, they become more and more accurate over the years, which is great, obviously, with more data. So that is the foundation of any forecast. But those forecasts and any kind of tweaking to the forecast that experts or meteorologists do, one of the key tools for operations at a DOT, and most northern DOTs have some form of a decision support system, whether it's a formalized maintenance decision support system or the term MDSS, like most folks have heard. The example on the right here is actually Iteris's MDSS, which not only looks at the weather, it has forecasts, and then says what you're going to need to do is start performing Operation X at 6 a.m., 6 p.m., noon, whatever it might be. It gives you some guidance on what to do. And those decision support systems are really been critical in helping bring down the cost of winter operations and being more effective and timely in those operations procedures. Includes staffing, equipment, materials, all those things I mentioned at the very beginning that go into that cost of winter maintenance operations. So, like I said, it talks about what to apply, when to apply, and how much to apply. They're provided by a human forecaster. In some cases, in our case, my small company, we actually do more of a human decision support system and then work alongside the folks that do the actual maintenance, operators and snowplow drivers. Others use software that give them recommendations on how much salt to put down and so forth. But either way, they all have the basic same funnel of information from big picture weather down to what's going on the roadway, and then helping support decisions by the DOT or other client. Now going into a forecast side of it. So we know what's happening. We have instrumentation that can watch roadways and help figure out what to do when it comes to operations. But forecasting out there, there's some critical parameters that we discuss in the book. Of course, precipitation type, but duration and intensity. So once again, that 2, 3, 4 inches of snow in a 24-hour period that comes down as light snow very uniformly, not as much of a problem as 4 inches in an hour when it's exactly 32 degrees or 31 degrees. And the sun's going up or the sun's going down, it's going to freeze that. Wind direction, speed have considerable impacts on drifting, and that secondary freeze that you often see on roadways. Air temperature, humidity, obviously is huge, as is air temperature. The road and subsurface temperatures, the pavement, and then expected conditions relevant to operations. I think most of us know that a road acts differently after any kind of precipitation, whether you have a lot of traffic or very little traffic. So that is also a key. And then also, there's always a little bit of uncertainty, and saying that there's uncertainty in the weather world is kind of I'm sure there are a few people giggling out there. Of course, the old joke is, you can be, who else can be wrong this often and still have a job, right? Well, thermodynamics of big clouds in the atmosphere are really, really tough. We don't always know exactly what's going to happen or when it's going to rain or why it's going to rain. But that level of uncertainty can be relayed to the client, and that client can know that I'm really certain that I'm okay keeping my guys or calling my guys in. But that level of uncertainty is also very critical in when and why you make a decision and what decision you ultimately make. So that has to kind of be an overlay of all these other parameters. Speaking a little more about forecast confidence, one of the big differences between atmospheric weather or your AccuWeather or what you see on TV, your local weatherman, is the confidence and how it's relayed, whether it's deterministic or probabilistic. So what you normally see, or what most people think of as a forecast, are probabilities. 40% chance of precipitation, where deterministic forecasting is more our goal when it comes to operational forecast. Deterministic means there's you have more an actual impact. The impact is going to be between the morning commute and the afternoon commute, there's going to be a lot of accumulation, up to 3 inches, and it's probably going to be slick. So there's more. It's really focused more on the impact that's going to happen. Operational forecasts tend to be more deterministic for that reason. Storms are complex, as I say in here. Their terrain's complex, locations are complex. So making that determination is much more important because, once again, forecasting for the state of Utah, you can say the state of Utah is going to get hit by a storm, but that storm is going to have a much different impact in the city of Salt Lake City, in the valley, up at Park City, up in the mountains, mountain passes, and so forth. So hopefully that's pretty obvious to most of you, especially someplace like Alaska or wherever else the folks are from. You have a lot more variation in probably one city than I do here in Iowa, actual elevation-wise. Benefits of operational forecasting, they provide real value to agencies, and I'll get into talk a little bit more about the benefit cost side of it and some of the examples. But Dr. Shi, who is, was the lead author on this book, actually researched 10 years ago when he was at Montana State, I believe, that the benefit cost of using services like this paid themselves off 11 times over for just the maintenance department alone. That's not talking about human lives and traffic operations and the economic side of it. We're talking a typical storm. They're talking about $1 million per storm when it comes to potential costs and savings, versus loss to the economy in a place just like the state of Utah or the Salt Lake Valley. So the numbers are huge. The amount of money being used and the money being saved, it's huge, and so the need is important. This operation is important. Benefits obviously extend beyond maintenance, and sharing the forecast information with other agencies helps develop a broader knowledge. So what happens in a lot of states is the DOT has that role as being the pavement forecaster, but that also impacts other agencies, all the state agencies, the cities, so forth. They can help alert other safety type issues where it comes to flooding, avalanches, and so forth. So there are a lot of secondary and tertiary benefits from doing this sort of work that affect the broad area group of agencies across this area, state, or whatever. So that's road weather forecasting. So to give an idea of what we do as a company and other companies like us, and the old idea of having weather services that do that very focused, specific road weather forecaster that is kind of a niche for a DOT to have their road weather forecaster versus watching the news the night before. There's a big difference in those. One of the tools or group of tools that our forecasting group, private sector forecasting, the DOTs, whoever might own or implement the instrumentation, or what's called road weather information systems, or RWIS, refers to a group of environmental sensor stations or instruments that observe that near surface atmosphere and below the surface. And it's really specific to weather stations just for the roads, just like weather operation stations for airports that look at the runway and other atmospherics at the runway level. These are for roadway surfaces and can be very, very detailed, but they can also be very simple. I'll talk a little bit about some of the options from soup to nuts when it comes to RWIS. My company, for example, we are RWIS people. We do RWIS, we maintain RWIS, that sort of thing. There are other vendors out there, lots of folks that do it, and the world has changed when it comes to RWIS. I'll talk about that a little bit. But in general, I'm going to talk about what a traditional station has looked like. They're called weather stations. They can be called by any name, but it's all about this instrumentation. And a typical traditional RWIS site is set up on a tower sort of setting. Let me move that over here. Non-invasive or temperature conditioned road sensors. It can be something with infrared. We have a wind sensor, an anemometer looking at wind speed, radiation sensors, precipitation, visibility, snow depth, temperature, and RH, and then all the other instrumentation is on the surface and below the surface. It's a combination or a suite of instruments that are very specific to what's going on at that roadway surface. And that provides valuable information to weather forecasters that are therefore then doing this work for state agencies or local agencies. So they're critical in the success of these programs. Sorry, I'm trying to There we go. Here's a couple more views of Arwis. The one on the left, I believe, is in Minnesota. Once again, looking at a camera. Was also a part of an Arwis, or a lot more Arwis today have cameras, maybe not so 10, 20 years ago. But when I'm out talking to folks in the field or maintenance guys in my day-to-day work that I do, cameras are invaluable. And a lot of them say, we don't always understand the atmosphere, so what's going on with the other sensors. And they might not even trust the sensor that's very, very accurate. But everybody trusts cameras because they can see what's going on. Everybody trusts their own eyes. So those cameras are becoming invaluable and ubiquitous. And now we're starting to look at cameras where folks are using those camera images just like the human eye uses them to help these sensors, looking for variations in precipitation, what's going on with the visibility, etc. So that camera piece has become much more important, as are these other sensors shown here. On the far right, I'm 90% sure that Arwis is up in Alaska. That was given to my friend Jack Stickle years ago, gave me that. I should give him credit, sorry. The other is at the top of a mountain, I believe in Idaho, in a very snowy area, a cold area. But every weather station probably looks a little bit different. There's all kinds of types and instrumentation that can go on them. In the business of Arwis, you don't always need every sensor at every station. We're doing some work for Minnesota, and the whole idea was to save money and not have to put redundant information out. You might have an anemometer or a very accurate wind speed anemometer up at an airport that's 3 miles away from your Arwis, but you don't know anything about the road. But you don't need another anemometer out there at the Arwis because you have a pretty good idea if it's similar geography with topography. You already know what the wind speed is. Well, let's not over-instrument some of these, but they should be instrumented to what is specific to that need and what that location, whether that location is a problem area, put at a bridge or a place that freezes or high accident area, or it's representative, that this weather station is very representative for this 10-mile section of roadway. So that's also very important to determine what kinds of instrumentation are going to be used. Those Arwis that I have shown the last few pages, and I have an anemometer and an actual a non-invasive sensor, a condition sensor shown off to the right. In general, look at air temperature, relative humidity, in other words, how close the air is to saturation, which impacts all kinds of things with weather. Dew, frost point, temperature, wind speed, precip, the solar radiation, which is critical at different times of the year all over the country and the world. And then pavement surface temperature, freezing point, etc., subsurface temperature. Those are the kinds of measurements. I won't get into those too deep. Optional Arwis measurements, like I mentioned, visibility, sensors, barometric pressure. Cameras are, I'd almost put in the other list, but they're still somewhat optional. Snow depth sensors, water height sensors, these are ones that aren't as common on an Arwis. This slide's important maybe to read in the future, but sighting Arwis is very, very critical. As I mentioned a minute ago, a site can be a problem site that's very unique for that roadway section or stretch of roads, or it can be representative of that roadway section. So what it represents really determines what kind of instrumentation and how you understand and read that Arwis. Once again, there's a lot of non-traditional Arwis out there, portable Arwis, and I'll talk a little bit, such as the mobile Arwis here. This happens to be a looped Marwis, which is mobile Arwis. So this whole idea of not just having an individual station that's non-mobile station, getting a reading similar to those from a vehicle along a stretch of roadway. So more data points essentially, but balancing more data points versus accuracy is something that the world is finding. But they're getting better, and this mobile data collection is having a huge impact on winter operations or winter maintenance. I'll try to wrap up here the next few minutes here. It's almost a quarter till. Managing your sensor data. So putting up an Arwis isn't just like a one-time cost, obviously. Data and managing the data and managing the sensors themselves are critical. Utah has a very extensive network. They spend a lot of money on the network itself, on keeping it maintained. In order to do that, it costs a lot of money, but it costs a lot more money not to do it because once you get to the 11-to-1 benefit to cost of operations just for the maintenance department, it really has shown Utah and many other states now that investing and then keeping that investment in place with RWIS and continue reinvesting in the RWIS is worth it. So that routine calibration of the sensors and maintenance, making sure they're all working when they need to be. Quality control of the data. It is possible that data streams, they kind of drift over time. Looking at the data is the best way to determine if data's off. They can drift, and manufacturers even say that. They just need recalibration, that's all, in most cases. And then the thing a lot of folks leave out is the metadata. Understanding what's going on at that site, the other data. Are there a lot of trees in that area? Are there, what's going on in the environment around it? What is unique about this site and those sensors that might make readings look different than other readings around them, for example, and understand the environment. And that's states like Utah and others, Minnesota and others, have spent a lot of time just looking at looking at how to maintain those systems and the value of them. And that metadata is really critical. So I'd stress anybody that has an RWIS network or is putting systems in, that keeping track of that metadata and maintaining your networks are critical. So I'm going to stop there. That's kind of the way our chapter works. There is a conclusion to it, which kind of summarizes everything I've talked about, but I think we can kind of do that in a question and answer session. So if there are any questions for me, if anybody has any follow-up that I can either answer or pass on to a smarter person, do that now. So go ahead, folks, if you have any questions.